Hi guys. So this is a sort of a side thing. Um, for people who have had linear algebra is really the target audience of this. So what I'm going to tell you in this little clip is not at all needed for anything we would do. It's what you will learn after you take linear algebra. It gives you just maybe a slightly faster way. Well, it is a faster way to do this if you've already had linear algebra. So it's just a way, remember how when I worked out the cross product and I kind of distributed things and I kept the stuff and I watched the minus sign? Okay. There is an object in linear algebra which has all of the same kind of minus signs and it's anti-symmetric and it has all the same basic properties. And so this is a trick. It works only in 3 dimensions. In higher dimensions, there are faster ways to do it than what I was showing you. Excuse me. But even the meaning of what the cross product computes is different. I'll comment on that at the very end. You won't need it in this class. Okay. So first of all, in linear algebra, you learn about something called a determinant. Okay. So a determinant is an operation that you perform on square matrices. So a matrix is a list of numbers. We've seen them if you're having numerical methods computer programming with me. Sorry, we've had lists and arrays. A matrix is an array of an arrays, and you make sure that you have they're all kind of the same size. So you can write numbers out in 3 by 3 forms, or you could have 4 by 4, 5 by 5, 6 by 6. But it turns out you can have determinants of 6 by 6 things, but that determinant isn't related to the cross product in that case, not in a simple way. So a determinant of a matrix. Okay. So if I give you a 3 by 3 matrix, let's just say it has numbers A, B, C, D, E, F, G, H, and I. So this is a matrix, usually in linear algebra. I think people do that. And then let's suppose we want to take the determinant of that. Sometimes you say det of that. Sometimes people do weird double brackets, whatever. All right. Just use whatever notation you saw in linear algebra. I don't know. All right. When you do the process of taking the determinant, again, it seems like some random hodgepodge of this and that and this and that. What's really happening is you are identifying perpendicular pieces. That's what's really happening, just like in a cross product. Okay. So the recipe is as follows. The formula is you do what's called a cofactor expansion. So again, if you haven't had linear algebra, you won't know what any of this means. Okay. But whatever sits here in A, and in linear algebra class, you usually take it to be a number, but we can do the same process for anything. So A, and then you multiply it by the product here minus the product here. So it's A times the quantity EI minus FH. And then the rule is whenever you swap, or I can think of it as like jumping. Whenever you jump to the next, whenever you make a jump, you get a minus sign. So you jump and you get a minus sign. And now I do the expansion. And then when you do these determinants, I take the determinant kind of centered on this element. I cross the row and column that it's in, and I look at the sub determinant, we call it, of what's left. So over here I had A, so I cross out the row and column with A, and I'm left with this little block. Now I'm on B, I cross them out, and I'm left with DI minus FG. And finally, I make another jump. So I had One minus sign when I made the first jump. Now I make another jump, so I get another minus sign. Two negative signs giving me a plus. And I get C times, okay, I cross out row and column with C, and I get DH minus EG. Okay, that is the answer for a determinant of an arbitrary 3 by 3 matrix. I'm not going to go into matrix theory and why this is a reasonable thing or eigenvalues and all that. It doesn't matter for us. What I want to do is to show you that the same process will compute the cross product. The only thing that's a little funky is that rather than having a matrix formed out of just numbers, it's kind of like what you do in Mathematica, where you can build objects and you can matrices and lists of arbitrary things. So here we're going to put X hat in the top, Y hat, and Z hat. And then I want to compute A cross B, and I claim it's going to equal the determinant of the following matrix. A cross B, and I put A along the first row, so it's going to be AX, AY, AZ, and then I put B along the bottom, BX, BY, BZ. Now, with some practice, you can do these determinants in your head. After you take linear algebra, you can kind of look at it and say, boom, 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 pull it all together, get your answer. Let's work it out here. It's the same process. Take the determinant. I take the thing here, X hat, times, cross it out, the determinant of what's left behind. Boom, minus boom. So I get A, Y, B, Z, minus A, Z, B, Y. And I jump over one. I get minus Y hat times, cross them out, and I get AX, BZ, minus AZ, BX. Awesome. And then I jump over one more, and I get Z hat, and I get AX minus, or times BY minus AY, BX. And if you compare this result to what we had in the last video, you'll see they're exactly the same. And this is the faster way to think of it. I feel like in 3D, you can just kind of hop around on this grid and you can pull out the numbers in a more or less straightforward way. All right, that's how you can use determinant. So if you already know what a determinant is, that gives you a determinant, or the cross product. There's no advantage, or there's no physical difference. It's just a way to repackage things. You know, you take linear algebra and you learn all these tricks about matrices. So you've already, if you've taken linear algebra, you've done the work, and you know, this may seem easier, but it's only easier if you put in all that work. When you do the cross product the way I was showing you, and if you really prove that formula the way I showed you, you're doing that same work that you do in linear algebra, but you'd have to do it every single time. So the determinant just allows you to kind of see the pattern that's always there, and there's no reason to reinvent the wheel every single time. The determinant takes care of that, counting those minus signs for you. In higher dimensions, it's trickier than that. In higher dimensions, well, first of all, you don't really, the cross product doesn't really exist. If you take there's no way to if you're in 4 dimensions, say, there's no natural way to take 2 vectors and pair them and produce another vector. There's kind of no geometric way to do that that's sensible. In fact, you can't do a vector in the same plane, because that would give you, that's really what the vector sum gives you. So you need some other way to pair up 2 vectors to produce something else. And in fact, if you think about it, well, the concept that's going to survive, in fact, in say 4 dimensions, is that the extension or the analog of a cross product in 4 dimensions is something associated with the perpendicular directions, but in fact, it's not the cross product between 2 vectors. In that case, doesn't define a vector. It actually defines a plane. Okay, it defines a perpendicular sheet. And so in D dimensions, the analog of a cross product between 2 vectors defines something which lives in D minus 2 dimensions. So in 4 dimensions, the analog of a cross product gives you something that lives in, or something that is a 2-dimensional kind of beast. So it's a sheet. The analog of a cross product in 5 dimensions would be, so 5 minus 2, that would be a volume. And if you're doing string theory, the analog of a cross product would give you something which is I don't know, it lives in, it's an 8-dimensional, it's like an 8-dimensional volume, whatever that means. Interestingly, then we can apply that same formula in 2 dimensions. So if you take a cross product between 2 vectors in a plane, if you embed that plane, we've seen that you think of the answers living in the 3rd direction, so like x hat cross y hat gives z hat. But what if you only lived in 2 dimensions? You wouldn't know what z hat was. And in fact, it would just be a number, right? So if you had 2 vectors, the cross product between 2 vectors in 2 dimensions, it's something that lives in 0 dimensions. So it's just a scalar, just a number. It has no geometric size associated with it. And that can happen, especially when we think about magnetic fields in a plane. You can kind of think about that as just a number defined in the plane. So anyway, that's a little bit of extra, I don't know, culture for those of you who have had linear algebra. And if you haven't, I don't know, I suppose it's like vitamins. It doesn't hurt. So anyways, there you go.